Of the 100 billion stars in our galaxy, Betelgeuse has to be one of the most intriguing. Floating around 700 light-years away in the Orion constellation, this red supergiant is some 1,000 times larger than our Sun, with a 1.2 billion kilometer diameter. For those keeping count, that places Betelgeuse's photosphere, the star's outer shell, at about the same radius as the orbit of Jupiter when compared to our solar system. Oh, and some scientists thought it was going to explode there for a minute. However, Betelgeuse's size and hypothetically explosive tendency aren't its only head-scratching attributes. This massive celestial body, with a diameter roughly 1,000 times that of our Sun, has been exhibiting peculiar behavior that challenges our understanding of stellar physics. Recent observations suggest it is spinning at a mind-bending rate, much faster than a star its size should be able to. This finding then sparks intense scientific curiosity and prompted researchers to re-examine the fundamental laws governing stellar evolution. Join us as we dig deep into the unusual behavior of Betelgeuse and the secrets behind its seemingly impossible rotational speed. First, you should know that almost all measurements of motion in astronomy make use of a law of physics called the Doppler effect. This change in the wavelength or frequency, color, or pitch of a wave emitted by a moving source was first described by physicist Christian Doppler in 1842, and many of us experience the Doppler effect firsthand almost every day without even realizing it. We've all heard how a siren changes as a police car rushes past, with a high-pitched siren upon approach, shifting to a lower pitch as the vehicle speeds away. This apparent change in pitch to the observer is due to sound waves effectively bunching together or spreading out. It is all relative as the siren's frequency doesn't change. As the police car travels towards you, the number of waves is compressed into a decreasing distance. This increase in the frequency of sound waves that you hear causes the pitch to seem higher. Whereas then the ambulance goes past you and moves away. The sound waves are spread across an increasing distance, thus reducing the frequency you hear, so the pitch seems lower. This principle of the Doppler effect applies to light as well as sound. Red shift and blue shift describe the change in the frequency of a light wave depending on whether an object is moving toward or away from us. When an object is moving away from us, the light from the object is known as red shift, and when an object is moving towards us, the light from the object is known as blue shift. Astronomers use redshift and blue shift to deduce how far an object is away from Earth. The concept is key to charting the universe's expansion. To understand redshift and blue shift, first, you need to remember that visible light is a spectrum of color, each with a different wavelength. According to NASA, violet has the shortest wavelength at around 380 nanometers, and red has the longest at around 700 nanometers. When an object such as a star moves away from us, it is red-shifted, as the wavelength of light is stretched, so the light is seen as shifted towards the red end of the spectrum. Scientists also use this method to measure the rotational speed of Betelgeuse. Renowned as one of the brightest stars in the northern hemisphere over Earth, the giant red star well studied for study. But as observations of its dimming show, that doesn't mean it isn't capable of delivering surprises. At roughly 10 million years old, Betelgeuse is much younger than our nearly 5 billion-year-old Sun. But while it is much younger, it is also much more massive, and will burn through its materials faster and will therefore have a shorter lifespan than a star like our Sun. Betelgeuse is around 700 light-years away. This means that it takes the light from this star about 700 years to reach Earth. So if you see Betelgeuse in the night sky, you're seeing the star from about 700 years ago. Aside from its unmistakable color, Betelgeuse is particularly easy to spot because of its brightness. It is often the 10th brightest star in the sky. If the Sun and Betelgeuse were the same distance from us, we'd see Betelgeuse shine 100,000 times more brightly. Betelgeuse is also one of the largest stars visible to the unaided eye. With a diameter greater than 1.2 billion kilometers, Betelgeuse is over 1,000 times larger than the Sun. So, if the Sun and Betelgeuse were swapped and the red supergiant was placed at the heart of the solar system, it would engulf Mercury, Venus, Earth, and Mars, with its atmosphere extending all the way out to the orbit of Jupiter. Such massive stars are expected to have relatively sedate rotation speeds. This is because when stars puff out and expand during their red giant phase, the conservation of angular momentum suggests their rotation should slow. This is similar to an ice skater on Earth lowering and spreading out their arms to slow down their spins. But recent observations of Betelgeuse, particularly those made with ALMA, an observatory comprised of 66 radio antennas that together form a single telescope located in northern Chile, have created a mystery about the red supergiant. The latest data showed that Betelgeuse is rotating at around 5 kilometers per second. That's around 8 times as fast as a jet fighter. Not only that, but the investigation with ALMA also revealed that while half of Betelgeuse appears to be approaching Earth, the other appears to be receding. It was this so-called dipolar radial velocity map on the outer layer of Betelgeuse that scientists interpreted as rapid rotation. However, this interpretation hinges on Betelgeuse being considered a perfectly round sphere, and this isn't the case. The surface of the red supergiant star is turbulent with boiling bubbles. Some of those bubbles, in fact, are as large as Earth's entire orbit around the Sun. These bubbles, powered by a heat transfer mechanism called convection, can rise and fall at speeds as great as 30 km/s, around 3 times as fast as the Orion spacecraft, the crew vehicle of the Artemis mission. To analyze this precise, bubbly picture of Betelgeuse, the team developed a new post-processing computer package to simulate synthetic ALMA images and compare them with 3D radiation hydrodynamic simulations of non-rotating red supergiant stars. This revealed that a cluster of boiling bubbles rising on one side of Betelgeuse, as another cluster falls on the other, would create a dipolar radial velocity map. This convection would be blurred in actual ALMA observations, the team says, making it indistinguishable from rapid rotation. In fact, the crew found that in around 90% of their simulations, Betelgeuse would be interpreted as rotating at tens of thousands of miles per hour because of this large-scale boiling on the red supergiant's surface. Should the team's modeling be wrong, however, there may be other explanations. For instance, it could indicate the red supergiant star engaged in some stellar cannibalism long ago. To solve this conundrum, scientists will need higher resolution data to determine if Betelgeuse's high rotational speed is actually a convective mirage. And luckily, such data was captured back in 2022 and is being processed. Once analyzed, the data could solve one of Betelgeuse's many mysteries. But even if the mystery surrounding Betelgeuse's rotation rate is solved, there is so much we still don't understand about gigantic boiling stars like Betelgeuse. One of these biggest mysteries is related to the brightness of this bulk star. Though it has almost always appeared as one of the brightest stars in the sky, its ranking among those stars has risen and fallen over time. Betelgeuse, it seems, fades and brightens in the sky, waxing and waning in strength over the years. Over the past 2 centuries, modern telescopes have uncovered a scientific reason for this. Betelgeuse is a pulsating star, one that shrinks and expands roughly once every 400 days. That, in turn, creates a variation in its brightness, albeit one that appears to be unsteadily laid over various longer-term cycles. However, recently, that cycle seems to have broken down. Early in 2019, Betelgeuse began to dim, just as researchers had expected. But instead of later beginning to brighten again, it kept getting darker and darker. By the end of the year, the star was fainter than it had been in at least a century, and so had lost its place among the 20 brightest stars. This behavior baffled scientists and led to speculation that a supernova was imminent. Could it be, some wondered, the sign of an unexpected disturbance rippling through the star, an indicator of dramatic changes to come? Within weeks, though, the star was brightening again, and by August 2020, it had apparently returned to normal. No supernova followed, at least not yet, and the star has not dimmed so dramatically again. Whatever had happened to the star, it seemed to be a temporary hiccup, a blip that had soon passed. In the end, it was a weather satellite that provided the answers. By chance, the Japanese Himawari 8 satellite had caught images of Betelgeuse stretching over a period of several months. For astronomers, this was a stroke of good luck, offering them a chance to see exactly how the star had changed in the weeks leading up to the great dimming of 2019. Betelgeuse, they found, had blown out a vast belch of stellar material. As this moved away from the star and cooled, it formed a dust cloud, blocking much of the light coming from the star. From Earth, we saw this as an unexpected darkening of the star. Although the dust cloud has since dissipated, and Betelgeuse has regained its usual brightness, the star has not been quite its old self since. Its 400-day brightness oscillation period has halved to 200 days, and on top of that, in the spring of 2023, the star began to brighten beyond its usual peak luminosity. But later months, Betelgeuse has faded again. Indeed it is. But unlike the great dimming of 2019-20, its waning so far has been modest. As of March, Betelgeuse has dipped nearly half a magnitude since late January. That may not sound like much, especially given the star's variable nature, but the red supergiant star is currently the faintest it's been in the past 2 years. Could it be at the threshold of another major dimming? If so, is it a sign of instability in this old red supergiant star? And could it mean Betelgeuse will explode soon? Well, previously, the answer has been maybe today, maybe 1,000 years from now. But a paper published in June 2023 suggested not thousands of years, but tens of years as the timescale for Betelgeuse's going supernova. Tens of years. It's a long time in human terms, but in cosmic terms, that's a blink of an eye. That means the red supergiant's life will be short and frenzied. Our sun, currently approaching the midway point of its life, can expect to live for 10 billion years, but Betelgeuse will only live for roughly 1,000th of that time. Even compared to other stars, that's an astoundingly short life for a star. And this is because of its mass. Betelgeuse has around 20 times the mass of our sun, and that means it has burned through its fuel very, very quickly indeed. And one day, just like every other star, Betelgeuse will run out of fuel. It's the fate of every star. But how massive a star defines its end? The nuclear fusion at the heart of our sun, for example, is fusing hydrogen into helium. Once all the helium is gone, it'll transform into a red giant and get hot enough to fuse helium into carbon, which in turn will combine with helium to form oxygen. Eventually, gravity will lose, and the sun's outer layers will dissipate away, leaving a dead white dwarf. This isn't the fate that awaits Betelgeuse. Betelgeuse is so massive and hot in the center that it is able to fuse much heavier elements like calcium and silicon. It's a red supergiant, and it is destined for a far more vicious death. But what would happen if Betelgeuse burst right now? Supernova explosions are so bright that they briefly outshine entire galaxies. With current-sensitive telescopes, astronomers can spot supernovas in the farthermost reaches of the universe. Multiple such explosions can be detected within a single night, but most of them are so far away that we mere mortals can't notice. But a Betelgeuse supernova would be different. Due to the star's close proximity, the explosion would be so bright that it would be visible even in the daytime. Once Betelgeuse was to go supernova, our first surefire signature would come in the form of high-energy neutrinos flooding our neutrino detectors all over the world in a burst spanning some 10 to 15 seconds. There would literally be millions, perhaps even tens of millions, of neutrinos picked up all at once by these observatories. A few hours later, when the first energetic ripples created by this cataclysm reached the star's outer layers, a breakout of photons would reach us, a swift spike that increased Betelgeuse's optical brightness tremendously. All of a sudden, the luminosity of Betelgeuse would spike by about a factor of 7,000 from its previously steady value. It would go from one of the brightest stars in the night sky to the brightness of a thin crescent moon, about 40 times brighter than the planet Venus. That peak brightness would only last for a few minutes before falling again back to being just about 5 times brighter than it previously was, but then the traditional supernova rise begins. Over a time period of approximately 10 days, the brightness of Betelgeuse will gradually rise, eventually becoming about as bright as the full moon. Its brightness will surpass all the stars and planets after about an hour, will reach that of a half moon in 3 days, and will reach its maximum brightness after approximately 10 days. To sky watchers across the globe, Betelgeuse will appear to be even brighter than the full moon, as instead of being spread out over half a degree like the full moon, all of its brightness will be concentrated into a single, solitary, saturated point. As a Type II supernova, Betelgeuse will remain bright for a very long time, although there are large variations within these classes of supernovae for exactly how bright they become and how bright they remain over long periods of time. The supernova, after reaching maximum brightness, will slowly begin to fade over the time span of about a month, becoming about as dim as a half moon after 30 days' time. Over the next 2 months, however, its brightness will plateau, becoming dimmer only to instruments and astrophotographers. The typical human eye will not be able to discern a change in brightness over this time. All of a sudden, though, the brightness will drop precipitously over the 4th month since detonation. It will go back to barely being brighter than Venus by the end of that time. And finally, over the next year or two, it will gradually fade out of existence, with the supernova remnant visible only through telescopes. Interestingly, at peak brightness, Betelgeuse will shine approximately as brightly as 10 billion suns all packed together. By the time a couple of years have gone by, it will be too faint to be seen with the naked human eye. The reason the supernova remains so bright for the first 3 months or so isn't even from the explosion itself, but rather from a combination of radioactive decays and the expanding gases in the supernova remnant. During those first 3 months or so, Betelgeuse will be so bright that it will be clearly visible during the day as well as the night. Only after the 4th month or so will it become a nighttime-only object. And as it begins to fade from its brightness to look like a normal star once again, the extended structures should remain illuminated through a telescope for decades, centuries, and even millennia to come. It will become the closest supernova remnant in recorded history, and will remain a spectacular sight and astronomical object of study for generations to come. In short, whenever Betelgeuse finally does go supernova, it will become the most witnessed astronomical event in human history, visible to nearly all of Earth's inhabitants. Over the course of the next couple of millennia, the majesty of this tempestuous star, which has shone above every generation of humans ever to walk the Earth, will fade from our view forever. Of course, such an event has happened before. Roughly twice a century, astronomers calculate, a star explodes somewhere in our galaxy, but most do so far away, and so their light is obscured by clouds of dust and gas, rendering them invisible to the human eye. Historical records speak of just 4 visible supernovae in the past millennium, the last of which erupted in 1604. So, just a few people are lucky enough to see one. Even fewer will see one as bright as that promised by Betelgeuse, of which only one in recorded history, that of the year 1006, comes close. Records speak of a new star appearing at the end of March that year, burning strongly enough to be seen during the day and at night, casting shadows on the ground. For months it shone, appearing brighter and larger than even Venus. But in those days, observers knew little of what caused such guest stars to suddenly appear in the sky. In China, astrologers interpreted it as a sign of prosperity, reporting it to the emperor as an auspicious omen. Others saw it as a portent of famine and plague, a warning of a coming disaster. 9 centuries later, with the advantages offered by modern telescopes, a pair of American astronomers found the resting place of that long-ago supernova. It lies some 7,000 light-years from Earth, marked by an expanding shell of glowing gas. At the heart of it should be a remnant, either a black hole or a neutron star, formed in the heat of the supernova, yet so far at least, nothing has been spotted. Betelgeuse, at a distance of roughly 700 light-years, is 10 times closer than the 1006 supernova. It lies close enough indeed that some commentators worry its demise may have dramatic effects on our planet. Shock waves from such a nearby supernova, they fret, could slam into the solar system. Radiation from it could strip the ozone layer and poison the atmosphere. This nightmare scenario is unlikely. Betelgeuse is close, but not that close. A supernova would need to detonate within 100 light-years or so to be a real danger, and at present, no known star presents such a risk. Similar events have probably happened in the past, but on a timescale of once every 100 million years or so. Then the supernova of Betelgeuse promises to be a spectacular event, one that humanity can enjoy without fear of famine or plague. When it erupts, it will shine far more brightly than the event of 1006, more brightly, in all probability, than any other supernova since the dawn of civilization. With a promise of such a spectacle, it is no surprise that sky watchers wish for Betelgeuse to die. But as told, we will probably see it happen sometime in the next 100,000 years, a blink in cosmic terms, but unfortunately an extremely long time for mortal humankind. On the other hand, it is worth noting that when we study stars, we are looking at the past. Because Betelgeuse is 640 light-years away from us, it's interesting to think that it could have gone supernova any time since the 14th century, and we still wouldn't know about it. Either way, when humans finally see Betelgeuse's last moments, it will certainly be a magnificent celestial spectacle like no other. Put Betelgeuse aside, a new study suggests dark comets, which are near-Earth asteroids that behave like comets and could contain water ice, have mostly come from the asteroid belt between Mars and Jupiter and could make up as much as 60% of all near-Earth objects. Dark comets were first revealed in 2023, when a team led by Darryl Seligman of Cornell University identified 6 of them based on their anomalous motions. Asteroids follow orbits dictated by the sun's gravity. However, the 6 objects identified by Seligman's team display an orbital acceleration that cannot be explained by gravity alone. Such motion is not unfamiliar. We see it all the time with comets, which receive an extra push when they heat up and their ices sublimate, creating outgassing that can speed them up and alter their orbital trajectory, while the material that is outgassed forms a comet's tail and coma, the fuzzy cloud around the head of a comet. However, the 6 objects found by Seligman's team don't have a coma or tail. In fact, they have no visible outgassing at all, but their non-gravitational acceleration tells us that there must be some, presumably caused by the sublimation of subsurface ice, hence the nickname dark comets. Now, new research led by Astor Taylor of the University of Michigan, whose team includes Seligman, has found where these dark comets come from. By applying dynamical modeling techniques in computer simulations, Taylor's group was able to replicate the orbits of the dark comets, showing that they can end up in near-Earth orbits if they start out in the inner region of the asteroid belt. There is one possible exception. One of the discovered objects, the dark comet 2003 RM, could have once been what's called a Jupiter family comet, which typically have orbits that take them out as far as Jupiter before coming back in toward Earth. Another possibility is that it came from the outer edge of the asteroid belt instead. The findings solidify an earlier theory dating back to the 1980s that predicts there's a lot of water ice buried beneath the surface of objects in the asteroid belt. NASA's Dawn mission found ice on the dwarf planet Ceres, and strong hints of ice on the asteroid Vesta, both of which are the main asteroid belt. However, both Ceres and Vesta are much larger than most asteroids, and are considered to be the remains of protoplanets that were never accreted into fully fledged planets back at the dawn of the solar system. It was not clear if water ice is commonly present on much smaller asteroids, but the dark comet studies suggest that it is. The new findings are supported by previous observations of other objects that blur the line between comets and asteroids. So-called active asteroids are bodies in the asteroid belt that behave like comets, with visible outgassing and even small tails. However, their existence is mysterious. Are they asteroids that have accrued some ice, or are they comets from the edge of the solar system that have become trapped in the asteroid belt on their journey around the sun? The connection between active asteroids and dark comets is still being debated, but Taylor suggests that dark comets and possibly active asteroids could be a source of Earth's water. In the words of Taylor, "We don't know if these dark comets delivered water to Earth. We can't say that, but we can say that there is still a debate over how exactly the Earth's water got here. The work we've done has shown that this is another pathway to get ice from somewhere in the rest of the solar system to the Earth's environment." Taylor's team's calculations and modeling suggests that up to 60% of the near-Earth object population could be dark comets. Even the asteroid Bennu, recently visited by NASA's OSIRIS-REx mission, displayed some subtle outgassing activity when seen up close, implying that asteroids that outgas at levels too minor to be seen from Earth could be common. The lifetime of objects that orbit near Earth is only about 10 million years before gravitational forces scatter them into the Sun, toward Jupiter, or into a planet. So dark comets must be being constantly replenished with fresh objects from the asteroid belt to maintain the current numbers near Earth. With the exception of 2003 RM, dark comets are typically small, just a few dozen meters or so across, and are spinning quickly. The outgassing, which must be a fairly modest amount since we cannot see it directly, is also to blame for the fast rotations and small sizes of the dark comets. When patches of ice begin to sublimate, the resulting vapor bursts through the asteroid's surface and creates plumes of outgassing material from different locations on an asteroid. The momentum imparted by this outgassing can send the asteroid spinning fast enough to eventually break apart. The resulting fragments then also begin spinning as they outgas, and gradually they whittle themselves down to the size of the tiny dark comets that we see today. It's also possible that we've seen a dark comet before. In 2017, the first known interstellar object, Oumuamua, passed through the inner solar system. It experienced non-gravitational acceleration despite no comet-like outgassing having been detected. This led to several hypotheses as to what Oumuamua was. One of leading explanations, from Alan Jackson and Steve Desch of Arizona State University, proposes that Oumuamua is a chunk of nitrogen ice. When New Horizons flew past Pluto in 2015, it observed areas such as Sputnik Planitia that were essentially frozen nitrogen lakes. Jackson and Desch suggested that Oumuamua could be a fragment of nitrogen ice that a giant impact blasted off of a Pluto-like body. Outgassing nitrogen, sublimated by the heat of the sun, would have given Oumuamua the necessary extra push. Nitrogen also would have given Oumuamua an albedo of 0.64, which is more reflective than a typical comet. So Oumuamua would have had to be smaller than thought to have appeared so faint. Jackson and Desch calculated that if Oumuamua was made from nitrogen ice, the object's dimensions would be just 45 by 44 by 7.5 meters. Another possible explanation, proposed by Daryl Seligman of Cornell University and Jennifer Bergner of the University of California, Berkeley, is that while Oumuamua was traveling through interstellar space, cosmic rays might have interacted with ice on the surface, liberating the hydrogen from some of the water molecules and creating a supply of hydrogen gas locked up in amorphous water ice. Per Seligman and Bergner's hypothesis, when Oumuamua passed by the Sun, the interstellar object was heated, though not enough to cause the water ice to evaporate. Instead, the heating changed the structure of the ice crystals, thus allowing the hydrogen to escape at a rate of 10 to 800 grams per second, and giving Oumuamua the observed push. This would also explain why Oumuamua had no visible dust tail, because the dust would have still been trapped in the water ice. Meanwhile, a wild hypothesis put forward by Harvard astronomers Avi Loeb and Shmuel Bialy proposes that the non-gravitational acceleration is evidence that Oumuamua was a spaceship with a solar sail. However, the discovery of natural dark comets native to our solar system and which also exhibit non-gravitational acceleration while having no visible outgassing is too similar to Oumuamua to not draw comparisons. It therefore does not seem outlandish to suggest that Oumuamua was also some form of dark comet rather than a spaceship. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.